As the car continues its transition from a hardware-driven mission to a software-driven electronic device, the auto industry's competitive rules are being rewritten. The engine was the technology and the engineering core of 20th century automobile. But today, the software, the large computing power, and the advanced sensors are increasingly stepped into that role, and that enable most of the today's innovations, from efficiency to connectivity to autonomous driving to electrification and shared mobility. However, as the importance of electronics and its associated software has grown, so has the complexity. Take the exploding number of software lines of code contained in a modern day car. In 1970s, it was hardly 100 lines of code. But in 2010, it has grown to 10 million lines of software code in a premium German car. But whereas in 2016, that has grown drastically to 15 times more and approximately 150 million lines of software code. As we all aware that the future car is mainly driven by software and the massive software stack. There will not be steering wheel and of course no driver. That's why the future autonomous car we call the software car. On the other hand, autonomous driving could transform the way we live, work and play, creating safer and efficient roads. These cars today are fitted with increasing number of environmental sensors such as radar, lidar, camera and ultrasonics, and they perform multitude of tasks. Sensor fusion can function and improve the ADAS performance drastically. Sensor fusion in next-gen autonomous vehicles could function in all weather conditions with very high reliability. So, software is the main driver of the change in today's electromobility revolution. In this webinar, we will talk about our motivation for the technology with a quick introduction to autonomous driving, various levels and its timeline. We also talk about various sensors enabling autonomous driving, and then we deep dive into radar signal processing and also our differentiation in software and algorithms. We also talk about various challenges on which we are currently working on, and then the approaches for sensor fusion, and finally the solutions and the products offered at Invecas. Approximately 35 people will be dying in road accidents during this webinar. That's very sad, and it's very sad for all of us. Traffic injuries are the number one cause of death for young people globally, aged between 15 to 29 years. Moreover, 94% of these road accidents are happening due to human errors, such as bad perception of the environment, lack of knowledge of the driving environment, low training, like such as Sunday drivers and young drivers, and also socio-economic pressures, working load, and driver distractions. So the problem that we are trying to solve is to improve access to mobility without any fatalities. That's what a typical North American city would look like. Everybody commutes by car, and these cars are parked around in all the space which is available today. But with the advancements in the future, this space will be freed up, and this space can be used for various purposes. And in fact, you can increase more greenery, and then you can breathe more air. ADAS, or advanced driving system, can improve safety and enhances traffic coordination and removes the human factors and also reduces the insurance premiums. Traffic is one of the biggest reason for stress. With autonomous driving and congestion-free roads, the same thing can be converted into a productive time with positive aspect of life. The Society of Automotive Engineers had defined 6 levels of autonomy, starting with level 0 no automation to level 5 full automation. Whereas level 2 and level 3 and level 4 and 5, the higher the levels up, the higher the responsibility of system. As far as I am concerned, there are only 2 levels of autonomy. One is human-centered autonomy, wherein human is full responsible, whereas the full autonomy, where car is in complete responsibility in terms of legality, experience and algorithmic side. Autonomous driving systems consists of various number of sensors to perform both safety and comfort functions. such as like blind spot detection, lane departure warning, lane keep assist, adaptive cruise control, forward collision warning, emergency brake assist, rear cross traffic alert and warning systems, and also cross traffic alert functions. Whereas blind spot detection function can be done with short range radar and also sometimes with camera as well. Line departure warning is mainly done with cameras. Line keep assist is also done with either camera or radar. Adaptive cruise control functions and forward collision warning and emergency brake assist, they mainly done with radar, camera and LiDAR. And rear cross traffic alert and cross traffic alert are mainly done with camera sensors. All these sensors work cohesively to sense the environment and process those signals and plan the appropriate actions depends upon the objects encountered in front of the vehicle. Different sensors like radar, LiDAR, camera and ultrasound are fitted around the car to enable autonomous driving functions. Each sensor has its own advantages and disadvantages. For example, radar works in all weather conditions day and night 24/7. It also can work in rain, snow, fog conditions. It is also unobtrusive sensor, meaning it can be fitted behind any plastic or a bumper or also behind a windshield. And radar is a very low cost solution. But there is a problem with radar's resolution today, and there are experimental high bandwidth radars are there which can provide you the resolution required, which is for creating a high definition perception map. Whereas LiDAR creates a 3D environment model around the car. It is very mature and reliable, and its resolution is higher than radar today. And it may not work very well compared to radar in snow, rain and fog conditions. Also, LiDAR is very expensive today, but there are advancements in this technology like flash LiDAR and solid state LiDARs that may bring down the cost. Camera is very low cost solution and it has a very high resolution compared to both radar and LiDAR. Camera can give the color and texture required for the applications like traffic sign detection and all. And camera has a problem that it may not work very well in low light and bad light conditions and also night conditions. And also there is a demand for high computational power for both mission vision and then computer vision applications. Ultrasound is also another inexpensive sensor, and it works for very short distances at a very lower speeds of the car. For example, like rear park assist. At a higher speed, the wind blow can create false alarms for the sensor to function. There are also other sensors like GPS and odometer and then vehicle sensors, but they're all secondary in the context of ADAS and autonomous driving. As the higher the levels of autonomy goes up, so as the demand for redundancy and also the need for large number of these sensors to complement each other. Out of all the sensors, radar has gained a lot of importance because it can provide more reliably and accurate information about the targets encountered by the autonomous car, like the range, velocity, angle of arrival, and also the type of the target, that's called course classification. And of course, it works in all weather conditions, day and night, with a lower cost solution. Radar has become non-replaceable sensor in ADAS and autonomous driving context. It has been used to cross-validate other sensors' data. Depends upon the range, radar can be categorized into different radars for various applications. For example, ultra short range, a short range and mid range and a long range radar. Ultra short range radar is an emerging ADAS application for park assist systems. Driver assist features such as lane departure, blind spot warning employ short range radar, and current short range radar systems utilize 24 to 29 GHz frequency band, but there is a plan that this will be shifted towards 79 to 81 GHz band. And functions like automatic emergency braking and adaptive cruise control use long-range radar systems. Current long-range radar systems operate in 76 to 77 GHz frequency range. Higher the levels of automated driving demand higher range and resolution, so future front radar systems will likely use both 76 to 77 as well as 77 to 81 GHz frequencies and a combination of LR and mid-range radar systems in a multi-mode configuration mode. FMCW stands for Frequency Modulated Continuous Wave. FMCW radar estimates the range, velocity, angle of arrival of objects in front of the radar. At the heart of FMCW radar, there is a wave called chirp. A chirp is a sinusoidal waveform whose frequency varies linearly with time. The sine wave or the chirp waveform is linearly modulated with frequency. That's when we call frequency modulated continuous wave. In FMCW radar, the synthesizer generates a chirp. The chirp is transmitted by a transmit antenna, and the chirp is reflected off an object in front of the radar. The reflected chirp is received at the receive antenna. The received signal and the transmitted signal are mixed, and the resulting signal is called the IF signal or the beat frequency signal. The frequency proportional to the delay that the signal has traveled gives you the range. Also, the reflected signal have a Doppler frequency corresponding to the speed of the target, and the number of antennas on the receiver are going to give you the information necessary to estimate the direction of the targets. In order to be able to capture the Doppler, hence it's a very slow frequency, the idea is to have large number of chirps collected in a processing interval called coherent processing time. We have a signal sampled at fast time called the range scale stored in one dimension of the cube, and we also have a samples collected and stored in the slow time scale, which are stored in the other dimension of the cube. Also, we also stack them all the signals in the third dimension called the spatial dimension for all the receive antennas of the radar system. So, you can see that this data cube is actually the data given by the sensor will scale differently with resolution and the data points we collect. The higher the data we collect and the higher the resolution it will provide. So there are different types of FMCW radars available, such as like a single transmit antenna and then single receive antenna mode, that is what we call as a SIMO mode, and then we can also have a multiple transmit antennas and multiple receive antennas. This is what we have used in our development, that is also called a MIMO radar, and that enables the more number of receive antennas in terms of the MIMO capability for getting a higher resolution of the angle estimation. Let's get into the details of radar signal processing chain. Fast Fourier transforms are at the heart of FMCW radar signal processing. FFTs can directly estimate the range, velocity and angle of arrival of the targets in front of the radar. From the radar cube, if you apply FFT on the range dimension, the peak of the FFT will directly give you the range estimate. But on the other dimension of the radar cube across multiple chirps, if we apply the 2D FFT, that would give you the speed estimation, because the rate of change of phase is nothing but the frequency. That's how the 2D FFT estimation directly give you the speed of the target. On the other dimension, the rate of change of phase across the multiple antennas would give you the angle of arrival. Hence, the three-dimensional FFT on the cube would directly give us the angle of arrival estimation. In the middle, we have a 2D FFT plot which you see two red dots at different ranges and velocities. And in fact, what it shows is we have two different targets which are separated apart in range and also have two different speeds. The next phase in the process is the detection and done typically using CFAR. We call constant false alarm rate. This is basically an averaging and sorting kind of operation. In fact, you have a cell under test and that will be compared with its neighbors, either averaging the neighbors energy to the cell under test and then comparing, or you do some sorting and then do comparing the energy as well. At the end of this process, you will get a certain number of detections and this an input to the module of angle of arrival estimation. Also, the measured phase difference across multiple antennas can be used to estimate the angle of arrival of the object. After getting detections from CFAR, we cluster all the points detected using a density based clustering algorithm to a single larger object. Then we give the detected object's range velocity to a Kalman tracking filter. The Kalman filter is a recursive algorithm designed to estimate the true state of a system where only noisy observations and measurements are available. It contains a linear model for the process as well as a linear model for the measurement. The output of all this process is an object list, and this object list would be given to the next layers of the software stack, and the list consists of the characteristics of the target like range, speed and then direction. The conventional FFT techniques are limited in resolution due to various problems associated. For example, the picket fence effect and the straddle losses, and also there is a relation between a modulation frequency and the beat frequency has to be a integer number. If that doesn't exist, their resolution is limited. In order to overcome this, we had come up with a novel approach in estimating the FFTs, which essentially gives the range, speed and the angle of arrival in FMCW radar. In this technique, we estimate the frequencies in two stages. In the first stage, the estimation is like a conventional FFT, but whereas in the second stage, we find the peaks and then we also find the boundaries for each peak, and then we use a minimization technique and an optimization technique to find the minimum within the boundaries. That ensures higher resolution than the conventional techniques which are limited to the bin resolution. Estimating the frequency is viewed as a min-max problem. The minimization is performed using a simple gold section univariate minimization technique without gradients. The minimization method finds the extreme values of a univariate function accurately. The algorithm works by successively narrowing the range of values inside which the extremum is known to exist. The technique derives its name from the fact that the algorithm maintains the function values for triples of points whose distances form a golden ratio. We have developed a complex phase processing radar with sub-wavelength accuracy and resolution, and we also developed a super resolution angle estimation techniques which goes beyond the theoretical limits, and we have also developed a interactive multimodal algorithm for accurate state estimation of maneuvering targets in nonlinear drive conditions. And the radar which we developed is a software defined multi-mode radar which can function as a short range to a mid range to a long range applications with the software configurable capability. We are also working on a high resolution radar imaging application with a third party RF and microwave front end. We use 4 such microwave front ends. Each has 3 TX and 4 RX antennas, and we cascade them to enable a much higher resolution capable sensor. In this configuration shown in the left side figure, that we cascaded 4 and then we build a 192 receive antenna capable system. In the middle, you see the higher the number of receivers, the narrower the resolution of the beam, and hence it will give you high resolution detection capability. Because the objective is that we would like to build a system which can perform as good as a LiDAR imaging, which is shown in the extreme right of the picture. In a short while from now, we would be able to demonstrate our software algorithms capability that we will be able to build a high resolution imaging radar which can potentially complement or replace some of the applications in the ADAS domain context. On the other side, there are challenges on the computational demands needed. Today, German premium vehicles have something close to 70 to 100 control devices. They are often developed for a specific use, such as infotainment, body controls, and so on and so on. The control devices are networked by way of highly complex tree of cables using multiple bus systems. For example, for the engine control, chassis, and infotainment, different communication protocols being used, including LIN, CAN, FlexRay, and most. So the number and the complexity of automotive SoCs, which as shown in the left side of the picture, is growing dramatically to fill the demand of new features in the next generation vehicles. The middle depicts various ADAS functions and relates to them to the type of sensing technology and also the type of hardware required to realize those functions are shown. ADAS domain controllers require high performance compute resources and DSPs to perform data processing and analysis, and perhaps chips that can support neural network computational needs when addressing level 4 and level 5 autonomous driving. The varied and unique list of applications are a testament that single chip solutions cannot meet the diverse requirements related to camera, radar, and sensor fusion. In fact, it's not a one size fits all the automotive SoCs. We also see on the right some trends towards consolidation of the ECUs taking place already, like the domain controllers for ADAS and autonomous driving, and also the domain controllers for the entire infotainment, and also for the body controllers and powertrain, so on and so on. We can see some of the trends today, but there may be new other solutions yet to be invented, as all the automotive OEMs wants the latest and the greatest in a very short time frame. It would be application specific IP or the hardware accelerated solutions. We all have the challenge to meet the demanding requirements of today's mobility revolution. Let's get into the details of sensor fusion. Multi-sensor data fusion is a multi-level, multifaceted process dealing with automatic detection, association, correlation, estimation, and a combination of data from single to multiple information sources. The result of the data fusion process helps users make decisions in complicated driving scenarios. Multi-sensor fusion will provide more reliable and accurate information that could be achieved using a single independent sensor. The integration or the fusion of redundant information can reduce overall uncertainty and thus serve to increase the accuracy with which the features are perceived by the system. Multiple sensors providing redundant information can serve to increase reliability in the case of sensor errors or the failures. So complementary information from multiple sensors will help to build the environment model perceived in a better way. Sensor fusion can be done at multiple levels such as high level, low level, and hierarchical level. High level is basically done at objects detection stage. For example, radar gives its object list and camera also gives its object list, and fusion is carried using the total objects and the tracks of these objects being extracted. The main difficulty when performing high-level sensor fusion is the data association problem. Given a set of high-level representation of objects tracks for every sensor, one must determine which of the tracks belong to the same object. It is also possible to perform sensor fusion in a hierarchical or a multi-level way, although it is not very popular in practice. Finally, sensor fusion can also be done at low level. The main reason to prefer low-level fusion approach is that the decision rule determining the final state of the map or the position of the objects is applied at a very last stage. This way, no information is lost in intermediate stages, which occurs in high-level sensor fusion approaches, where the system mainly consists of following subsystems or the modules. One is sensor layer, the other is perception layer, and the other is the decision making layer, and then finally the actuation or action layer. The sensor layer includes onboard environment monitoring sensors, inside driver monitoring sensor, and vehicle body sensors. For example, vehicle ego state and vehicle dynamics module. In general, the external sensors captures the surrounding environment related to the targets, for example, range and speed and extra. The in-cabin sensors will capture the driver's behavior and the drowsiness detection or the fatigue detection and extra. And whereas the vehicle sensors will estimate the vehicle state such as speed, acceleration, and then steering angle. Moving to the second subsystem, that is perception layer, this layer aims to give a realistic representation of the environment to the applications of the ADAS functions. It can be seen as an intermediate layer between the sensorial subsystem and the system functions. It includes sensor fusion of previous layers in order to model the environment and future situation assessment. The role of the perception layer is to carry out a perception enhancement of the external scenario and describe the environment and the traffic scenario, and also supports the specific needs of the ADAS system in the reconstruction of the environment. It acts as an intermediate layer between sensors and the ADAS functions. The third decision-making layer, as its name implies, perform decision carrying out one or several or the various driver assistants depending on the status of the previous layers. Decision-making agents have two functions. First, to generate a warning strategies for the warning systems such as route guide system, haptic alerts, and warning display devices. And the secondly, to plan the actions of the actuators to control the path of the host vehicle, such as steering, also the acceleration or the deceleration. The fourth one is the action layer, and this layer is responsible for handling the output from all the different applications in order to carry out appropriate warning and intervention strategies to pass the information and the suggestions or the alarms to the driver through a given HMI. In summary, it creates a comprehensive environment model by fusing various sensors in and around the car, computes the best driving strategy for maximum driver safety and convenience. It makes decisions and triggers actuators in the car. Now, let's explore how to build a high-resolution environment model using the general fusion framework discussed so far. It consists of sensor abstraction layer and also grid management subsystems. In sensor abstraction layer, we have sensor model. The task of the sensor model is to restore the original physical dimensions of the sensor readings, which are being subject of adding to the grid. Input sensor model will primarily applying a special smoothing function to the sensor measurement values like Gaussian blur function from image processing. The goal is to derive a inverse model function which restores all original physical properties of the real world object. We also do spatial correction to the measurements, as the processing of sensor values within a sensor and the transmission of these sensor signals to the high resolution environment model consumes a time. This means that the sensor reading by an ADC converter took place at an earlier time compared to an actual availability of this reading output signal at the HRE input interface. The faster the ego car is driving and the more the car is turning, the more is the error gets into these measurements. So we require an appropriate spatial correction before we add these readings to the grid map. Another block is the synchronization, which is actually performing the fusion of all the input data into the common joint intermediate grid in a vehicle coordinate system, which is then provided to the grid management. Then comes the map integration. The HRE shall be prepared also to include data from a digital map coming from navigational systems such as GPS. The render engine of the sensor abstraction layer actually transforms all sensor values into pixel values which are part of the layers of the update map. It also performs the interpretation of sensor values, performs the mapping of sensor values to layers available in the update map, transformation from sensor coordinate system to world coordinate system, performing the smoothing of sensor values using Gaussian smoothing function, and also performs the full spatial correction for sensor values due to the delay of the ego vehicle. Let's understand the dominance of various sensor combinations. Radar and camera most likely combination in next 5 to 8 years. Although solid state LiDAR and camera will be dominant in the long term when proven and integrated into mass production designs. The chart compares the capabilities of sensor combinations in the context of sensor fusion. Right now, the vehicle architectures are evolving from distributed to centralized processing as shown in left figure. In the centralized system architecture, most functional components of the autonomous driving system such as perception, planning and control are implemented into a single compute unit. The centralized system architecture has the benefits of simplifying the system configuration because all of the devices including the sensors and actuators are connected to the centralized computing unit. It requires a high computational capability because the algorithms of the autonomous driving system are large and complicated. It also lacks the scalability. Whereas in the distributed system architecture, the functional subcomponents of the autonomous driving system are implemented into several local computing units. Information from each computing unit is shared with the common communication system. There are many benefits of distributed system architecture compared with the centralized system architecture. By decentralizing the computational load into the sub-computing modules, the computational stability and efficiency of the system can improve. Cloud computing and 5G will add further to support the higher bandwidth required for massive data streaming. Not surprisingly, players across the digital automotive value chain are attempting to capitalize on innovations enabled through software and electronics. One consequence of these strategies move is that the vehicle architecture will become a service-oriented architecture based on generalized computing platforms. Developers are adding new connectivity solutions, applications, artificial intelligence elements, advanced analytics, and operating systems. The differentiation will not be in the traditional vehicle hardware anymore, but in the user interface and experience elements powered by software and advanced electronics. The advent of highly automated driving capabilities will require functionality, convergence, superior computing power, and a high degree of integration. Due to the high volume of data coming from sensors, enabling high performance networked connectivity has become a challenge that automotive SoC designers are overcoming with Ethernet. But these systems require more than performance. They require predictable latency and guaranteed bandwidth. We have a product developed in partnership with Tier 1 electric OEM, which is a multi-core, multi-precision, high-compute SoC primarily designed to transport high-speed raw data from sensors like radar, camera, and LiDAR to a central computer for developing level 3-4 self-driving car. We call it a iFabric and is a high bandwidth, low latency streaming network used in autonomous driving applications. It can carry 64 Gbps of data bidirectionally from different sensors such as radar or camera. This can be also used as a fail-safe network for improving redundancy using its primary and secondary ports, which essentially reduces the cabling work inside the car with a very low latency. The SoC has different subsystems for processing signals from radar and camera. The camera subsystem receives the packets from MIPI CSI2 and supports maximum image size up to 8 MP. The radar subsystem also receives the packets for the processing from MIPI CSI2, and the MIPI drives the data at a maximum of 500 megasamples per second per channel. We have 4 channels, hence the maximum sampling rate that would support is 200 megasamples per second. With a 16-bit precision, this goes up to 32 Gbps high-speed raw data transport capability using the SoC. We also have a custom radar DSP engine which is running at 1 GHz for fast complex fixed point FFT and also a standalone FFT accelerator engines. Our FFT accelerators running at 1 GHz can deliver 400,000 1024 point FFTs per second. We also have a ARM Cortex 32-bit processor which is running at 750 MHz with a 2.5 MB shared on-chip SRAM with 5 banks each of 512 KB. We also have a DSP engine which is running at 500 MHz. It supports both floating point arithmetic and vector processing required for the radar signal processing applications. We have implemented a multi-mode radar using our SoC using the dedicated FFT accelerators which are running at 1 GHz speed. For the entire radar signal chain, the execution time it took is 25 milliseconds, and that gives an update rate of 40 frames per second. This is very much high compared to state-of-the-art radar sensors available today. At Invecas, we take care of an end-to-end ASIC development including packaging and supply chain. With support for multiple foundries and latest nodes along with assembly partners, Invecas can help take the guesswork out of vendor selection and management while providing the most cost-effective solution. From there, we will work on to improve yield, negotiate year-on-year cost reductions, and manage RMA or FA fault arrival related issues that arise, all while maintaining a DPPM below 20. For example, our Vision SoC is fully programmable and combines the flexibility of software solutions with high performance and low power consumption dedicated hardware, which meets majority of today's computer vision demands for autonomous driving applications. Today, we have learned a bit of radar signal processing and sensor fusion strategies. If you have any questions, please feel free to ask me. I am more than happy to answer you. Thank you for your attention.